chord.
Number
All right.
42.
All right. Hang on. I lost what you said. Did you say chapter 32?
Oh, no, I said chapter 15, number 42. This is Physics 102.
Oh, yeah. Okay. Sorry. Yeah. Yeah. Oh, good. Good. Yeah. 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 Oh, now yeah, I should have put that together. All right. So, chapter 15, number what? 40?
42.
42. Hold off on your other ones. Let me start there. Because a couple things I need to do to get started. The first is to reactivate my phone here. And then, good. Now I need to connect it so I can share it with you. And let's see the other thing. Oh, I guess I need to hit share first. I was like, wait, why come it's not connecting? All right, so share. Okay, now it should work. Okay, so while that's connecting, let me go to my 102 homework assignment. Okay, good. And let me scroll down to, I'll fix the camera here. Scroll down to chapter 15, and you say number 42.
Yes.
All right, good. So 15, number 42. And let me just read it here. It says, draw the diagram representing a standing wave pattern for the fourth harmonic of a rope fixed at both ends. Okay, so there's a lot of scenarios that could happen with a rope or a string. If you tie it on each end, I'll make this kind of a wall here. And if you shake it, you'll get like these humps that will vibrate. And because the end of it are tied, both ends have to be one of these locations, which we call nodes.
Right.
Okay, so there's a bunch of possibilities. We could go from one node to the next, and so this whole thing would be one loop.
Right.
Okay.
And would that be considered the first harmonic?
Yes, very good. That's what I was building up to.
Okay.
Yeah, so when you start numbering them, that's the first. So when they say 4 harmonics, they mean you would have 4 of these humps. So it would look something like this, where you would have one hump, then a second, then a third, and then a fourth. And sometimes we like to then draw a moment later where it would look like this, and hopefully our drawings aren't confusing because it's not doing both of these at the same time. Then a moment later, it maybe looks like this. And then a moment later, it looks like this. And maybe I better stop drawing because with 4 different moments in time, that can get confusing. But that's often the way we draw it, 4 different moments in time. And in this case, since it's the 4th harmonic, there would be 4 humps. And since it's fixed on both ends would be a node. There are cases where maybe one end, instead of being tied, was put on like a metal loop and it could slide up and down. And so the end would be one of these
antinodes.
Yeah, an antinode. Good, good. Yeah, it sounds like you're getting the idea of the wording.
Yeah.
But when it says how many nodes are there, which is the question, then not counting the end, and some people count the end, so there's not a clear definition, but for the most part, I would call it 3. because there would be this point, and this point that don't go up. But I'll tell you what, why don't I look at the solutions here? What are the solutions? Because you could call it 3, but you could also call it 5. And let's see what the book does. The book says, oh, see, the book called them 5, but good. The book not only says 5, but they clarify it. They say there are 5 nodes, including the endpoints.
Oh,
Actually,
okay.
that's a really good answer. 5 nodes, including the endpoints, or you could say 3 nodes, excluding the endpoints.
Ah.
Yeah.
All right.
That was a really good answer.
Cool.
If I just say 3 or 5, that you always wonder if they're counting the endpoints. Nice. Oh, good. All right, you said you had another one?
Yeah, I do. So I would just put n equals 3 or 5, depending on how I wanted to, which one I decide.
Yeah. Just make sure you put including the endpoint or excluding the endpoint. I really like that. That makes it really clear. And so for a test question, that would leave no doubt in my mind that they understand. Yeah.
I see.
Oh yeah.
It kind of confuses me though, because I have here, you did this diagram during your lecture where, or maybe I can just turn my camera on and show you.
Oh, sure. Here, let me give you a chance to share. And by the way,
well, I can just turn my camera on. You don't have to. There we
go. Oh, okay.
All right. So you see how the n equals 1, and then n equals 2, and then n equals 3.
N equals 1. Yeah.
That's the harmonic, right?
Yeah.
Oh, but that's not the number of nodes.
Right. It's the number of humps, not the number of nodes.
Okay. So then I couldn't put n equals 3.
So for a fourth harmonic, if you draw 4 humps, you'll see that there are 5 nodes when you count the ends. So that's what a node is these points that don't move.
But when you put n equals 1, that's not counting nodes. That's counting harmonics.
Yeah, it's counting right. I would say it's counting the number of humps, but it's also labeling the harmonic.
Oh, okay. Okay, so I'm just gonna put 3 nodes. All right, and then okay, so my next question is number 48.
I'm sorry, you cut out a little bit. 40 what?
Just the next one, number 48.
Oh, next one. Okay, 48. All right, let me switch.
I think I was confused because I didn't understand what a harmonic was, but now it seems simple to me because I get what a harmonic is.
Yeah, and like don't beat yourself up. I think this is the hardest material, just understanding the pictures. And the other one is, yes, harmonics. And you want to know something even worse, and maybe I shouldn't even tell you this because I think the book stays away from it, is there's another phrase that people like to use called overtones. And an overtone is a harmonic minus 1.
Oh, God.
So if somebody says, find the 3rd overtone, that means the 4th harmonic.
Oh, why?
Well, because in music, so if you're talking about sound waves, the instrument itself is playing a note. So you call that its note, it's fundamental. And all the other frequencies are overtones above it. And so the first one, the fundamental, is what we call the first harmonic. Then the second harmonic would be the first overtone. It would be a tone that's above and beyond what the note you're playing.
Yeah, that's a little beyond me right now.
Yeah, like I said, I probably shouldn't have brought that up. Okay.
All right. So let's see. On the 4th harmonic.
Isn't that physics 123?
Yeah, 123. When you get to physics 123, yeah, we will. use the word harmonics as well as the word overtones.
All right. Well, 121 is I'm taking next semester.
Yeah. So you got. Don't stress it. You'll do that one
Okay.
next semester.
All right.
Then you'll do 122 in the fall, and then you'll do 123 the following spring.
I don't know if my degree goes that far.
Oh yeah, I apologize. Yeah, you may not have to do that much. Right. And so so you may not go that far. All right, so let me see if I can answer yours. And you're probably right. Now that you understand the word harmonic, it might make more sense. But I'm just gonna write here number 48. It says, how does the wavelength of the fourth harmonic on the rope with both ends fixed compared to that of a second harmonic?
Okay.
All right, so I'm going to draw both of them. And of course, the fourth harmonic is kind of that same picture there, but I'm going to draw it again and just go, oh, I should make it bigger so you can see it better. All right. So let me draw the fourth harmonic again. And the fourth harmonic would mean that there are 4 humps. And as we just talked about, there would be 3 nodes, not counting the ends, or 5 counting the ends. And let me just draw it this way. I know in the earlier problem, I drew it at different moments in time, but now that I know you got a good understanding of that, let me just draw at one moment in time. And so it's kind of like a snapshot of it. So that's the fourth harmonic. Let me draw right below it a second harmonic. Now, a second harmonic would mean 2 humps.
Right.
So it would go up like this and then down like that. And if the question was asking how many nodes, we might say, well, there's 1 node, not counting the ends, or there's 3 nodes counting the ends. That's not our question. Our question is to compare the wavelength. So if you said L was the length of this rope here, then in this fourth harmonic, you can see this would be 1 wavelength right here. So I would say wavelength equals 1/2 of the whole length. Or maybe to say it the same another way is I've got 2 wavelengths in here.
I see.
So 1 wavelength is half the length of the rope. But if you look at
then the second harmonic is just 1 wavelength.
Yeah. So I would say that the fourth harmonic, the wavelength is half as much as the second harmonic.
Okay.
Yeah.
Now, I guess, I don't know. I'm just like, is there an actual length attributed to that, or would you have to know more about the wave?
Yeah. You can't give a number here because they just say a rope. Now, if you really had, let's say I did this in the classroom and I tied the rope to one wall and the other wall, then I would know that the length is 10 meters. So then I would know the wavelength is 5 meters. But
okay, so you can have a fourth harmonic that is like really, really long just because the medium it's in is really long.
Say that again.
So you can have like a really, really long rope that's still vibrating at the fourth harmonic.
Yeah. So if you can imagine something like this, let's say I had a really, really long rope and I went out to a football stadium and I tie it to one goalpost right here. That little goalpost. And so that the cross beam, and I stretch the rope all the way to the other field goal, way out to here. And then I shake it so that it looks like this pattern. I would still call it the fourth harmonic. And its wavelength would be half the length. But let's see, from goalpost to goalpost, isn't that 120 yards?
I
Because
see.
the football field is 100 yards, and then the end zone is 10 on each
bit more
side.
than that because the goalposts are not. It's probably more like 130 yards.
Oh, but don't they curl in for that? The post is here, and then they curl in like that.
Yeah. The pole itself is supposed to be lined up with the back of the end zone.
Yeah. Well, that's what I meant. I'm sorry. I meant you were tying it to the
Okay.
post itself, not
Oh.
the. Yeah, but you're right. For safety reasons, they like to put this a little further out so you don't crash into it when you're playing the game.
Mm-hmm.
Anyways, but depending on where you tie it, it is 120 or more.
Okay.
I'll just call it 120. So that would be my wavelength would be, 60 meters for something that looked like this. I mean, 60 yards.
Okay.
And
Now
then
my
for this,
question is, a flute can play a fourth harmonic, but it has a much shorter wavelength, but it's the same ratio.
oh yeah, good point. Yeah, right. So things like a flute.
It's the same fourth harmonic, but it's much shorter just in
Right.
general because.
Right. And short wavelength sounds very high pitched. So things like flutes sound very high.
So what would you say is the difference? It's the actual length of the wavelength, even though the ratio is the same?
Yeah. The definitely for the case of a. Now I want to be a little careful. You picked flute, but I think a flute does not have ropes or strings inside.
Right.
So maybe a better example.
A guitar versus a bass.
Yeah,
Okay.
that'd be a better example.
Okay.
Yeah.
So the difference between the fourth harmonic on a guitar and the fourth harmonic on a bass is the actual length of the wavelength.
Yeah.
But so then you would say the pitch is different?
And that's true too, but let me be a little careful with that because the pitch is the frequency, and
Right.
that's velocity divided by the wavelength. So let me just, to make it simple, let's just say the velocity is the same on the string. The velocity of the string is the same on the guitar as the bass.
Okay.
See, in reality, that may not be true, okay? Because the speed is based upon how much tension you have. And usually you put more tension in a guitar string than a bass string.
Okay. But for simplicity, we're just going to call it the same velocity.
Yeah. So for simplicity, if the velocity is the same, then what you are saying is if the wavelength is bigger in the bass, then a number in the denominator that's bigger gives you a smaller frequency, which means a lower tone. And so, as the name implies, a bass plays your bass frequencies.
Mm.
And then for the guitar, you might say, actually, let's go smaller than the guitar. What's that little Hawaiian thing? The ukulele.
Yeah, ukulele.
Yeah. So then I would do the opposite for the ukulele. I would cross out big for the wavelength and put small. And therefore the frequency would be the big.
So it'd be a lot of hertz.
Yeah, well, a lot of hertz. Mm-hmm. And
a lot of hertz. So it'd be a different tone, but it'd be the same frequency.
Well, I would say, I think what you want is it's the same harmonic. It's the fourth harmonic, but it is a different frequency. It is a different wavelength.
Okay. Oh, okay. All right. That makes sense.
Mm-hmm, but it's the same pattern.
Uh-huh. Okay. Yeah, that clears it up. All right. Well, I have some more questions.
Yeah. Well, fire away.
All right. This one's chapter 16.
Okay.
Number 19.
Chapter 16, number 19.
Yes.
All right. Let me scroll down here. I'll even put here chapter 16, number 19. Yeah, you guys, these last two chapters are a little bit.
Yeah, they're hard.
Harder, yeah. Yeah, a little bit of a rude awakening here. But that's good. Okay, 19. How come I can't find 19? Is it an exercise?
It's an exercise, yes.
Oh, okay. Let me go down. All right, there it is. All right. So it says, what harmonic frequencies are possible in a closed organ pipe? All right. Now, this, I'm going to have to expand a little bit on this picture. The last two questions you've been asking me have been about a string or a rope, and both ends were tied, so both ends were nodes.
Mm-hmm.
Okay. When it comes to your sound tubes, your wind instruments, and so in this case, a pipe organ, let me draw a pipe on its side. I know that usually pipe organs have their pipes in a vertical fashion. But so I can compare it to what I've been drawing, let me draw the pipe sideways. And for a pipe organ, you could let both ends of the pipe be open, or you can close one end. You would never close both ends. If you close both ends, the sound is trapped in the pipe. So when it comes to sound tubes, we never talk about closed on both ends. It doesn't make any sense.
Mm-hmm.
I say that because the word here they did is they said closed. That means one side is closed, but the other side is open.
Mm-hmm.
Some books use the phrase closed hyphen open to indicate they're talking about both sides of the tube, which means you could have either an open or closed open. You can never have closed.
Okay.
So that's important in just understanding the names, and that's what could be I don't know if that was a problem for you, but you kind of like you were questioning the harmonic word. You know, what does a harmonic mean? I'm trying to point out what they say closed pipe organ. They mean one side is closed, the other side is open.
Yeah, so it's a node to an antinode.
Very good. Very good.
So my question, so I have a question. Does that mean, can you still produce a fourth harmonic on that?
Okay. Well, let's talk. You can. And here's where the terminology doesn't fit as well. So you can kind of question this for a second here, but let me just draw a standing wave here for a moment. Because if I were to draw one option, let's see, and how many did this say? It said, what harmonic frequencies are possible in a closed organ pipe that is 1 meter long? Okay, so what I could do, let me just pick one place that is the closed side, as you said would be a node. So let me call this the closed side. And when I look at a standing wave pattern, then one option is that the open is right here at the first antinode. But another option is that the open end represents that one.
Mm-hmm.
Another option is it represents that one.
Mm.
Another is that one.
Yeah.
And there's no limit to this. There's an infinite number. So the way the author writes it is going to make it hard to answer because really there's an infinite number. Okay. But that's okay. We'll use some tricks from math here in a second. But let me draw a picture. So the first one could look like this. It could be a node on this side and it arcs up and stops right there. You see, it doesn't make a complete arch. like was required in the other two problems we were doing. The other two problems required us to go from a node to a node, so we had to have a full arch.
Yeah.
So here we only have a small piece of it.
Right.
Now, I'll talk about the math in a second, but let me draw a picture.
So that's 1/4 of a wavelength.
Okay, right, you got the math. So let me do this. Let me say the length of the tube is L, which we know for this problem is 1 meter. I'll just call it L for the moment.
Okay.
But as you said, that would represent 1/4 of a wavelength. Exactly.
Right.
Okay. Now look at the second pattern that could occur. The second pattern that's possible is we got a node here, and we have to go to an antinode. And the other antinode would be meaning that there would be a full hump and another quarter in here.
Right.
So that would be L equals, it's a little harder to see.
It looks like
You see-
3/4.
Yeah, I like to do this. I like to split the first hump in half and go 1/4, 2/4, 3/4. Yep,
Okay.
3/4 of a wavelength. All right. And this is very visual, so that's why I'm trying to draw these pictures.
No,
Because
yeah, it's good.
you don't see the visual picture, you can't do the math. Okay, now watch this one. This would be from the node, and then let's see, the next antinode would be this one. So I would have 2 humps and a quarter. All right, so I'll make 1 hump, another hump, and a quarter. So L would equal to what?
1 1/4.
Okay, but to see the pattern a little better, how about I write that as 5/4?
Okay.
1, 2, 3, 4, 5. And maybe now you begin to see the pattern. You see, the first pattern is a quarter, and then every time after that, we are going to have to go 2 more quarters each time. So we will go from 1/4 to 3/4 to 5/4. Next one would be
7/4.
and then 9/4, and then 11/4. So I kind of like to write it this way. L would be equal to m over 4 lambda, where m is either a 1, a 3, a 5, a 7, a 9, 11, ...
Okay.
Okay. All right. So
So-
that's kind of the basic physics of it. Now I can finally get to the question. It says what frequencies are possible. Okay, so frequency is the velocity divided by the wavelengths. So let me rewrite this equation in terms of the wavelength. I would bring the 4 to the other side, so I had 4 over L. I would then divide by M, and that would equal wavelength. So again, the question would be a little bit easier if they had asked me what are the different wavelengths that are possible, because then I would just put in different values for M. I'd go M equal 1, M equal 3, M equal 5, M equal 7. But they asked me for the frequencies. So that's why down here, I'm going to put this equation for wavelength. I'm going to put my 4L over M. And now I'm going to take a little bit of math, because in math, you make the top a fraction, the bottom is already a fraction, and then you flip it and multiply. So in the top, I have an M and a V, and I'm going to just write them in reverse order. And in the bottom, I have 4L. And to do one more step, I'm going to put in my values. Since they're talking about a pipe organ, they're talking about sound waves probably at room temperature. So that's that 300.
So we know the velocity.
Yeah, 344. We also know how long the pipe is. I've been calling it L, but they made it very clear, 1 meter long.
Mm-hmm.
So if I get out my calculator and do the 344 divided by 4, I get M times 86. And I could either leave it like a math equation where M then can equal 1, 3, 5, 7, ... Or I could start putting in some values. If I put in M equal to 1, I would get 86.
And that'd be 86 hertz.
Yes, and we're talking about frequency. Thank you. I should put my units here, hertz.
Got it. Okay.
If I put in a 3, I would go 3 times 86. So 258 hertz. I could go 4 times 86. That's 430 hertz. And then you can just put ...
Okay. So I have a follow-up question. When you're playing music, are you trying to match your frequencies or are you trying to match your harmonics?
Oh, okay. So let me stay in the category of wind instruments since we're doing a pipe organ here. But you mentioned a flute a little while ago.
Mm-hmm.
I would put these in the same category. And when somebody, what I'm trying to say is, you don't really control this, but it's actually all of these are going on at the same time. And what you mostly hear is the fundamental one. There are some exceptions to that. The truth is, you're going to hear the one that plays the loudest.
Okay.
So in a pipe organ, the one that plays the loudest is the fundamental. But these other ones are also there. And that's what gives an organ its unique sound. Because if I were to play an organ and a flute, even though I play the same notes, they will sound a little different.
Yeah.
And the reason why is their fundamental frequency is the same, but these higher frequencies are there and they are different percentage of loudness.
So
I don't know what an organ is, but I'm gonna do this. Actually, I might turn to your textbook for a second, because your textbook gives a nice little chart. Let me scroll down. This must be chapter 16, where he does this. I don't see it. Maybe I'm remembering a different class. Okay. Never mind. I thought it had a little chart. Oh, here it is. He kind of has a little chart, but on it's figure 16-4, he shows how a violin has all, and he shows and that's a string, of course. So he shows the first, the second, the third, the fourth, and the fifth harmonic.
What page is it?
Page 336.
Okay.
But sadly, it wasn't quite what I was looking for, but it's a start in that direction because he's saying
I
that
see
all
it.
of these go on at the same time, but he's also trying to illustrate in the picture that the first harmonic has the biggest amplitude.
Oh, okay.
He
Yeah,
put-
that makes sense.
He draws it a little higher, and it's in picture B.
So like when you pluck a guitar string,
Uh-huh.
like they all ring out, but the initial ring is kind of like the strongest one because it like dampens as it gets.
Yeah. Well, yeah, but I'm not even talking about the dampening. That's true too. But even when you pluck it, it will. Let's see if I can kind of show this on the video. If I took a string and the first harmonic looked like this, and the second harmonic wasn't as big, might look like this. I'm trying to say that these two are happening at the same time. So if you could take a photograph of the string, it wouldn't really look like this. And it wouldn't really look like the second harmonic. It would look more like this. It would be the first harmonic with the second on top of that. And then underneath it like that.
Wow.
So so if I add these two together, it equals that.
Uh-huh. And so you
Okay.
add them all together, and that's what the string actually looks like?
Right. And so the string, if you actually took a photograph of this string, it probably would look like wah, 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 like that.
Wow.
And so it's trying to say it's doing all of these at the same time. And so your ear would, of course, pick up the loudest one. And so let's say that was the musical note G. So this would be playing it would be twice G, which would be the next octave up if you're into music. So if this is G3, this would now become G4. It would be
Okay.
twice the frequency. Then the next harmonic, well, the fourth harmonic would be G5 because it would be doubled and then doubled again. The third harmonic, I don't know what it would be. It would be 1.5 times the frequency of G3, and I'm not sure where that comes out to be. And so you would hear all of these things. Mostly you would hear the G, and you would have, taken the guitar and played the note G with it. But the guitar would also be playing these other notes. And if you switched from the guitar and went to the violin and still played a G, the same thing would be going on, but these higher, I'm going to use the word overtones, would have a different percentage of intensity than the guitar. So it would sound very close, but you could still be able to know somebody was playing a violin versus playing a guitar.
Right. Okay. And then my final question is, and then how do you match notes between a flute and a guitar?
Okay, so let's say a flute and a guitar are each going to play G.
Uh-huh.
Okay. So let's see. So I'm going to go 100% for the note G for the guitar. But for the flute, which is also playing the note G, this is mostly what you would hear. So they sound almost the same, okay? But the next harmonic, and if I could call this the first overtone, the guitar would play, and I'll just call it the next octave up, G4, would be playing maybe at about 10% the intensity of the original note you're playing.
Okay.
Whereas the flute might be playing at 40% of it.
Hmm.
So you, as you listen to them, because they're playing the same note, their fundamental one, the first harmonic, is the same, and you wouldn't really be able to tell any difference at this point between the guitar and the flute. You would say, oh yeah, they're both playing the note G. But because they have the other harmonics in there,
You can tell that they're a different instrument.
and they're playing with a different intensity,
Hmm.
you would be able to tell that, okay, that sounds a little different to me. And I've learned to know that that's a flute.
Oh.
And this one sounds a little different. So that is the guitar.
And so even though the flute goes from node to antinode, you can still play the fourth harmonic?
Oh, now, okay. So now okay. I wondered if that was buried in your question. I did not explain something here. I was treating them as, I'm not saying this well. I was treating them both really as stringed instruments.
Mm-hmm.
Okay. Just to emphasize that the reason you hear them different is they're different intensities. But yes, you have something else going on here. And that is, one is a string instrument and one is a wind instrument.
Mm-hmm.
Now, the flute, though, I don't think is like our organ problem. A flute actually has an opened at the end, and then it also has an opened where you blow the air in.
Right.
So I think the flute needs to be treated as a opened
Antinode,
sound tube.
antinode.
And right, and the antinode actually has the same pattern as the strings.
Oh, interesting.
So what I said is not wrong, but I wanted just to clarify there is a difference between them, but they would each play the second and the third and the fourth and the fifth. If you have a closed organ, then you only play the first, the third, the fifth, the seventh, the ninth. That's what we saw back when we were doing this.
So there are certain harmonics an organ can't play.
Right, if it's closed. Now, some organ pipes are opened on both ends.
Oh.
And some are closed.
So you'll have an organ with closed pipes and open pipes? Or it's all, either they're all closed or all open?
Ooh, I am not sure about that. I know you can have them where they're all closed or all open. The problem with my understanding is that the problem with closed on one end is the pipes have to be really long. And I guess depending on your definition, I've heard it say they sound better, but they're really long. So unless you're in a cathedral that has a ceiling that is 5 stories high, you need to do a smaller pipes, and you have to have open on both ends. Although 5 stories is pretty tall. It seems like if you were in a big church with a tall steeple, you got at least 3 stories in there. It seems like you would get a lot in there.
All right. Well, I think that clears a lot of it up for me.
Good. Yeah, and even a lot of other questions that weren't really, but yeah, you're getting into which is good. I mean, this is what makes to me science exciting, where you begin to see how it applies in the real world. But you've crossed the line from the physics of sound waves to what we call the physics of music. We used to have a class called the physics of music. was called Physics 104. Physics 104. It was the physics of music, and it was required by all music majors.
Yeah, I'm into music, so this is super interesting to me.
Ah, good.
Cool. All right. Thank you so much, Professor.
Okay. You bet.
All right. Have a nice one.
All right. You too. All right. Oh, hey, it looks like we're getting to about break time too, huh, Daniel? And, oh, hey, who popped in here?
You can ignore my question in chat. I ended up figuring it out.
Ah, okay. Good. All right. Oh, let me write down those questions that I was helping them with so that I can make a video of it here. So let's see. What was that last one? Was it 1 meter long, number 19, chapter 16? Okay, good. Yeah, so some good 102 questions here today. All right. Hey, if the rest of you have an important question you need to fire off, shoot it at me now. Otherwise,
Can you
I
go
think
over one piece of the question 58 for chapter 33.
chapter 33, number what?
58.
58?
Yeah, it's a super long question, but I only have a question on part C.
Okay. Let me, part C. Let me look that question up. Let's see, where are the questions for this class? Okay, and then, is that question that had like part A through H?
Yeah.
I was reading that and I was like, oh, wow. Look at all these things. Yeah. Okay, so part C says, find the current as a function of time when only switch 1 is open. Oh, okay. Well, for part C, as well as really all the parts, keep this in mind that you have a driving AC frequency and then the 3 elements in series, the resistor, the inductor, the capacitor. But I think what you already figured out in A and B, switches 1 and 2 are closed, so you really only have a resistor, okay? So when you go to calculate what we call the impedance, which depends on all 3 elements, for parts, and I know this wasn't your question, but A and B, you can just treat the impedance as just purely R. There is no inductors or capacitors in there. And so I'm going to say the same thing for part C. For part C, it says, find the current as a function of time after switch 1 is open. Okay, so the maximum current would then be equal to the maximum voltage divided by the impedance. And for part C, and it's just going to get harder with D, E, F, G, and H, is you just add the impedance here for, which switch are we opening here? Find the current as a function of time when only switch 1. So it would look like this. Z, the impedance, would be R squared plus XL squared, which would be R squared plus omega squared L squared.
Okay, that's right where I was getting confused.
Yeah, and so if we go to write the current as a function of time, the solution they worked out was the maximum current multiplied by sine of omega t plus the phase. And what I just did for you was this maximum. So I would go V max over and I would have an impedance that would involve a resistor and an inductor, but no capacitor, at least not yet. I think later on in parts C, D, and E, they do ask for it. But let me also point out the other piece of this puzzle. How much is it out of phase? That is, how much is the current out of phase with the voltage? That phase we got by taking the difference in reaction between the capacitor and the inductor and dividing it by the resistance. So for this problem, to get the phase, this would be the inverse tangent, or better word, arc tangent of, and for this problem, since switch 2 is still closed, we wouldn't have any reactance from our capacitor. That's why we ignored it in that step, and we can ignore it in this step. And then I would have this omega L over R. And so that should be the mathematical equation for the current as a function of time for part C.
So does it not matter if it's a sine or a cosine as long as we add the phase difference?
Oh, well, it should match what they gave you. And they gave you, oh, my apologies. They gave you cosine. So, which is interesting because in the textbook, they write it as sines. But yeah, now that I look closely at that figure, they list it as a cosine. So yeah, it should be a cosine.
Oh, okay.
That's my mistake for not writing it or not seeing what they wrote it as. All right. Hey, well, if that works for you,
Yep, thank you.
I'll take our little break right now and come back at 3, and we can do some more of these. Oh, I should have looked. Is there anything in the chat? I don't want to leave anybody hanging here. Okay. Good. All right. So I will see you guys at 3. How's that?